calculated in the sense that any inner product induces a norm, simply by taking the norm of x to be the square root of the inner product of x with itself. This is a fairly natural thing to do, and we can use this to compute lengths of vectors. For example, the dot product, which is an inner product, induces the Euclidean norm. That is, the norm of x is equal to the root of x transpose x. However, not every norm is induced by an inner product. The Manhattan norm, for example, is an example of a norm without a corresponding inner product. In what follows, we will focus on norms that are induced by inner products and introduce geometric concepts such as lengths, distances, and angles. We also have a theorem called the Cauchy-Schwarz inequality, where any inner product vector space, the induced norm satisfies the Cauchy-Schwarz inequality, that the absolute value of the inner product of x and y is less or equal to the norm of x times the norm of y. In geometry, we're often interested in lengths of vectors. We can now use inner products to compute these lengths. So let's consider the vector 1, 1. Using the dot product, the norm of x is the root of x transpose x, which is equal to the root of 1 squared plus 1 squared, which is equal to root 2. However, if we choose the inner product to be inner product of xy equals x transpose times the matrix 1, negative a half, 1 times y, we get that the norm of x is equal to the inner product, the root of the inner product of x with itself, which it turns out to be root 1 or just 1. So again, the length of a vector depends on the norm that you're using to calculate it. Well, it might seem counterintuitive to say that the distance between two things or the length of something is different depending on how we calculate it. We do this in real life. If we're walking to the store, we tend to think of the distance as the number of blocks east and west, and plus the number of blocks north and south that we walk in order to get from place A to place B. Whereas the distance as the crow flies might be more diagonal direction. We talk about, when we drive from city to city, we talk about the distance as being the length of the road that we travel, not the distance that an airplane would travel, which might be far more direct. So the idea that the same distance could be calculated to be two different values should be rather normal. Here we're going to talk about the distance between two vectors. So in an inner product space, the distance between vectors x and y is defined to be d of x and y, which is equal to the norm of x minus y, which is the square root of the inner product of x minus y with itself. This mapping D is called a metric. If we use the dot product as our inner product, then we have Euclidean distance. In general, a metric D, mapping a vector space to a vector space, satisfies the following properties. For every x and y in V, D is positive definite. That is, the distance between x and y is greater or equal to 0, and it's only equal to 0 if x is equal to y. It's symmetric. The distance from x to y is equal to the distance from y to x. And the triangle inequality. The distance from x to z is less than or equal to the distance from x to y, plus the distance from y to z. In this example, we want to prove that the Euclidean norm satisfies the properties of a metric. Here, the distance from x to y is the square root of the sum of the xi minus yi squareds. And that's greater or equal to 0 because all the terms under the square root are positive. When we take the root of a positive number, we get a positive number. And of course, this will only be 0 if all of those terms are equal to 0 inside the square root. That only happens when x equals y, which means that our distance, our Euclidean norm, is positive definite. We know that it's symmetric because if we look at the distance from x to y, that's the sum of the square root of xi minus yi squareds. And because of squaring, that's the same as yi minus xi squared. And so the order doesn't matter. Finally, we know that it satisfies the triangle inequality since the distance from x to z is equal to the norm of x minus z, which is equal to the norm of x minus y plus y minus z, which, by properties of norms, is less than or equal to the norm of x minus y plus the norm of y minus x, which happens to be equal to the distance from x to y plus the distance from y to z. In our next video, we're going to talk about how all of these ideas play a role in the angles between vectors. And in particular, when we can determine when vectors are orthogonal.